Today we're going to learn about the integrated rate law, section 12.4, and this word integrated comes from calculus. There's a symbol, looks like this, and it stands for an integral. And we literally are going to integrate the rate law. So for a first order rate law, we know rate is k a to the 1. That says the rate is first order in A. And rate for a reactant, the rate is the change in the concentration of a reactant over the change in time times -1, because the reactants are decreasing in time, but the rate is always a positive number, so this negative sign is there. And the right side is the same, Ka. Now, integration, we turn these deltas into a d. You don't need to know about integration. I'm just giving you some background. You can sort of fast forward through this part if you want to. I don't expect you to be able to do any of this. So we integrate both sides. First I get all the a's on the left side and the t on the right. We integrate both sides. And this is what you get when if you have a senior friend who's taking calculus and you say, hey, can you integrate this equation for me? They could probably do it, and you'll learn how to do it next year if you take calculus. Okay, when we integrate, we get a constant, and we can plug in information, and we learned that that constant is always the log of the initial concentration. So A0 is the initial concentration of A. Initial concentration of A. Whenever you see that little knot, it means initial concentration. All right, so that whole derivation you don't need to worry about. The thing that you must know is that for a first order reaction, this is what we call the integrated rate law, or the integral rate law. So we have rate laws, and we have integrated rate laws. We're going to go through 0, first, and second order integrated rate laws. I'm going to go through the derivation of how you get them, and you don't have to worry about the derivation if you want to just skip through. There's a summary of all the integrated rate laws later on, and you can skip this beginning part. Except there's some important notes here. All right, first, from this integrated rate law, if we know the initial concentration and the specific rate constant k, that k there is the specific rate constant, then I can solve for any concentration A at any particular time and vice versa. If I want to find a certain concentration, I can find the time at which it would happen, and if I'm given a certain time, I can find the concentration at that time. The second important piece here is this equation for the integrated rate law. It has the form y equals mx plus b, where ln of A would be your y, the specific rate constant would be your slope m, and log of A naught would be your b. And I've summarized that right here. So for y equals mx plus b, the y is ln of concentration of A, the slope is -k, and the constant b is the initial concentration of A. Now this gives us a way to determine, if we have experimental data, whether a reaction is first order, because right here we can graph log of A versus time. And if the reaction's first order, we will get a straight line, because this information right here. So if we plot log of A versus time, y is log of A, x is time, we'll get a straight line if the reaction is first order, and the slope of that straight line will be -k. So if we calculate the slope, take the opposite of what we get, we've got the rate constant. Okay, second order reaction, the rate would just be k a squared. We're going to do some miraculous calculus. This is the important equation right here. This is our second order integrated rate law. And again, these are all summarized later on. So if you want to skip through this and just look at the summary, that's fine. But you might notice this is the same y equals mx plus b. Our constant will be 1 over a naught. The slope will be positive k. And for the y value, we're going to plot 1 over the concentration versus time. So this looks exactly the same as the last one, except we have changed our y, what we're going to plot for y, and what b is. So, notes. If we know our initial concentration, and our specific rate constant, we can solve for the concentration of A at any time using this equation, and vice versa. And the equation also has the form of a straight line where y is 1 over a, the slope is positive k, and the intercept is 1 over a naught. All right, and now we can again use graphical methods. And notice in each of these explanations I've written in blue what we're going to graph versus time and the order, because I want you to see the differences between the different 0, first, and second order rates. So second order, we plot 1 over a versus time, and if we get a straight line, that means the reaction is second order, and the slope will be positive k this time. And it's just because of this equation that we get through calculus that the slope is plus k. I've often had students say, well, why is it plus k or minus k? It's just the mathematics of the equation. And now we're going to do 0 order. Okay, so 0 order rate law is, the rate is k a to the 0, which is just k. And we do this miraculous calculus work, and we come out with this rate law right here. This is the integrated rate law for a 0 order reaction. Right there. Okay, and again, it's y equals mx plus b. It has that form. Hang on, I'm going right here first. We're going to look at number 2 first. And this equation right here has the form y equals mx plus b, where y is our concentration of A, m is negative k, and b is our initial concentration. Okay. First note that we have here, just like the other ones, if we know the initial concentration and the specific rate constant, we can solve for the concentration at any time, or we can solve for the time given any concentration. All right, and now graphical methods. If we graph the concentration of A versus time, and we get a straight line, we know the reaction is 0 order. And the slope will be negative k, not positive k. So if we have concentration versus time data, we can plot concentration versus time, log of concentration versus time, 1 over concentration versus time. We see which graph gives us a straight line, and that gives us the order of the reaction. So I skipped ahead in the notes a couple pages. This is just a quick summary of all that I just showed you. So this first row is the rate laws for a 0, first, or second order reaction. And the second row is the integrated rate law. It's a summary of those 3 rate laws that are on the first 3 pages. And then on the next line, it's what do we need to plot in order to figure out what order a reaction is. So if we get a straight line when we plot concentration versus time, we know the reaction is 0 order. If we get a straight line when we plot log of concentration versus time, we know the reaction is first order. And if we plot 1 over concentration versus time, if we get a straight line, then we know the reaction is second order in the chemical that we are looking at. And we can always find the specific rate constant from these data by the slope. So 0 order, the slope is negative k. First order, the slope of that straight line would be negative k. Second order, the slope of that straight line would be k. Do not worry yet about the half-lives. We will talk about that in a bit. All right, now we're going to apply what we just learned. So we are given a bunch of experimental data, concentration versus time. We literally calculate the log of the concentration. For each of these concentrations, I calculate ln of the concentration. So I take ln of 21, and that's 3.04. ln of 19.5, and that is 2.97, etc. I go all the way down and I calculate the log of each concentration. Over here, I've calculated 1 over the concentration. So right here, this is 1 over 21. This is 1 over 19.5. And we do that all the way down. And then we plot our data and we see what we get. So I've got the plots of all the data. Don't worry, you don't need to do all your calculations there. I've done it all for you. So I've got 3 plots here. Concentration versus time, log of concentration versus time, and 1 over concentration versus time. And I check which one gave me a straight line. Do you see only one gave me a straight line? This one right here. Hopefully you've remembered, if I have concentration versus time giving me a straight line, do you know the order of the reaction? I'm going to tell you in a moment, but try to think about what it is or look through your notes. This reaction is 0 order in A because concentration of A versus time gives a straight line. Now, the slope of this line is negative k. So if I calculated the slope of that line, I would know the specific rate constant for this reaction would be the negative of the slope of this line right here. So all I need are concentration versus time data, and I can identify whether a reaction is 0, first, or second order, depending on which graph gave me a straight line. So let's look at the next set of data. We've got our experimental data. I've done all the calculations for you, and I've done the plots. And you figure out what's the order of this reaction. Which one gave us a straight line? We look, we see in this plot, 1 over concentration versus time gave a straight line. And so I check if this plot gives a straight line, the reaction must be a certain order, and the reaction must be second order in A. And I could calculate the slope of that line, and the slope of that line is the specific rate constant, positive k. All right, last one. Again, new experimental data. Somebody runs an experiment. You take their data, you calculate the log of all the concentrations, you calculate 1 over all the concentrations, you plot your data, and you see which graph gave me a straight line. Well, hopefully you can all see this is a straight line. If log of concentration versus time gives you a straight line, what's the order? Look it up, pause, do whatever you need to do. This reaction must be first order in A because log of concentration versus time gives a straight line. And the slope here is the negative of the specific rate constant. So the specific rate constant is just the negative of the slope. Okay, so far we've looked at graphical methods for how you can determine the order of a reaction if you have concentration versus time data. And now we're going to talk about half-life. And half-life, T1 half is defined as the time it takes for half of the initial concentration of any chemical to react. And we can derive an equation for the half-life for a first-order reaction. I'm going to derive this. If you don't care about the derivation, just shoot forward until you get the actual equation for it. All right, here's a derivation. By definition, the half-life is the time it takes for the initial concentration, A0, to become 1/2 of A0, because half of it is gone. We're going to substitute this into the integrated rate law for a first-order reaction. So we have our initial concentration. We're trying to find the time at which the concentration becomes 1/2 of the initial concentration. So the concentration at T1 half is 1/2 of A0. Solving this equation, I just take ln of A0 over to the left side. Now, some rules about logarithms. If I have log of x minus log of y, that is equal to log of x over y. That's a definition. So that's how I went from here to here. All right. Now, I've simplified the left side. And here's another definition. ln of a over b is negative ln of b over a. So if I take the reciprocal of what's in the log, I just change the sign. So I reciprocated 1/2 to get 2, and I changed the sign over here. That's why this is a plus now. Okay. Now I solve for T1 half, and right here is the equation of the half-life for a first-order reaction. That is only for a first-order reaction. And here's our summary again. And in this summary, there's another row in here we didn't talk about yet. I said we would do it later. It's the half-life equations. We are not going to be worrying about zero-order or second-order half-lives. We will only worry about half-lives for first-order reactions. And you might wonder, what's this 0.693? We found out that this is equal to ln of 2 over k. Well, if you put ln of 2 in your calculator, you will find that ln of 2 is equal to 0.693. I like to memorize this equation as ln of 2 over k, or if I ever forget it, I can always go through the derivation right here. We know that the half-life is when the concentration is half of the initial concentration, and I just calculate what T1 half is. All right, so let's do a problem. Problem-solving time. Blah, 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 blah. For the reaction, blah, 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 blah. Okay, let's see. How do we... Some key information here. Let's see, what's the key information? We have our specific rate constant. We know the reaction's first order. We know our initial concentration, and we're trying to find the concentration at 150 seconds. So we want to find concentration at 150 seconds. This is telling me I need to use my first order integrated rate law. There we go. And I'm going to plug in the data that I know. I know my K, I know my time. So I can plug in K, I can plug in time. Yep, I can plug in time. And I know my initial concentration. Plug it all in. Now I'm going to go through this pretty quickly, so you might want to pause at different points. I'm going to calculate everything on the right side, solve the right side. Now here's a trick. Right here. This is what some students don't quite understand. The inverse of log is the exponential. I have to do e to a logarithm, so e to the logarithm to solve this. And when I do e to the ln of x, I get back x. So when I do e raised to the negative 3.343, I get my concentration. And then we want to know, what is the half-life for the reaction in number 1? Well, half-life for a first-order reaction, I just have my equation, ln of 2 over k. I plug in my k value that was given in the problem, and I solve it, I get 100 seconds. Very easy. You do have to memorize this equation right here. Okay. New problem. If you want to pause, you can pause and try to solve this. I'm going to go through how to solve it. So part A, calculate K. I already know the half-life. I know the half-life. I can calculate K. That's easy. ln of 2 over K equals T1/2. I plug in my values and I get my K right here. Okay. Part B is a little more complicated. There's actually a very quick way to do this, but I'll show you that at the end. So for part B, we want to find out how long does it take for 75% of the reactant to go away. We have to recognize we're trying to find out when 25% is left. So we're trying to find the time when the concentration of A is 0.25 times the initial concentration. So I have my first order integrated rate law. Anytime you're given information about time, you're using the integrated rate law. Experimental data, you use just the rate law when you have different trials for experiments. Concentration versus time, we're doing integrated rate law. Anything with time, integrated rate law. All right, plug in my numbers. Pause if you want to try to solve this on your own. I've plugged in my numbers and I'm solving. And in this step, this might confuse you. Remember, if you have log of A minus log of B, it's the log of A over B. Okay? And the left side, I calculate, these cancel out, and I calculate ln of 0.25, and I get negative 1.39. And now, I just solve for my time, 40 minutes. All right, easier way to do this, the really easy method. Okay, if we have 25% left, you can recognize that means 1/4 is left. That's 2 half-lives, and I've given you an explanation here. So for 2 half-lives, first half-life, you're at half the concentration. The second half-life, you're at 1/2 of 1/2, which is 1/4 left, which is 25%. So the time you need would just be 2 half-lives, 2 times 20 minutes, 40 minutes. Notice we got the same exact answer, 40 minutes. Whoa! 40 minutes, 40 minutes, same answer, easy. Much easier way. All right, last problem. If you're just feeling done with this, it's okay to stop at this point. If you want to try one more problem, here we go. Okay, you've got all this information, but let's focus on what are we trying to find. We want to find the rate law, the integrated rate law, the value of the rate constant. We'll do that first. Let's see. What is the important information we've got? Well, we have our initial concentration, and we're told that a plot of log A versus time results in a straight line. What does that tell us? What does that tell us? Think about it. I'm going to tell you what it tells us. It tells us this is a first order reaction. So now I can very easily write the rate law and the integrated rate law. The rate constant, well, they told me the slope equals negative k, so I can get k as well. So I've just rewritten here what we just talked about. Since the ln of A versus time plot is linear, we know the reaction is first order in A. So here we go. Rate is Ka to the 1, first order. Integrated rate law, look it up. You're not going to be expected to memorize the integrated rate laws. Those are given to you on the AP exam. And K is the slope of the ln of A versus time graph. And this was our slope. Therefore, K is right here. Okay, next thing, we want to calculate the half-life. Well, wait, that's so easy. ln of 2 over K equals T1/2. Go ahead and pause if you want to calculate it on your own, or here it's solved out for you. T1/2 is just ln of 2 over K. I plug in my K value and solve 23.3 minutes. Okay, last thing. How much time is required for the concentration of A to decrease to 0.0025 molar? I will tell you right now there's a fast and a slow way. The slow way is to plug your data into the integrated rate law, and I'll show you how to do that. The fast way is to recognize how many half-lives you need to go from, this is 0.02 molar, to 0.0025 molar. How many times do you divide 0.02 into half to get 0.0025? But first, again, let's use the integrated rate law right there. So I plug all my information into the integrated rate law. This is the concentration for which we're trying to find the time. There's my initial concentration right there, and there's K. So now I'm just solving a mathematical equation. And again, pause if you want to solve it on your own. Here we go. We're just solving everything, going through the motions. And I find out 70 minutes. Okay? So I've shown you the math to go through each step. Here's the shortcut. The fast way, recognize the first half-life, we go from 0.2 to 0.01, 0.02 to 0.01. Next, I was missing a 0 there. We go from 0.01 to 0.005, and then we go from 0.005 to 0.0025. Missing some zeros in there. So we need 1, 2, 3 half-lives. That's 3 half-lives. So I just multiply the half-life by 3. 3 times t1/2 is 69.9 minutes, which our answer that we got was 70 minutes. Those are close enough. 69.9 versus the 70 that we got with the putting everything into the integrated rate law. That's it.